Hey everyone, and welcome back to AI Paper Podcast for another deep dive. Today we're looking at a paper that really caught our eye, and it's called "The FFT Strikes Back: An Efficient Alternative to Self-Attention."
Oh yeah, this one looks pretty interesting.
Yeah, we thought so too. And it's tackling a pretty familiar problem in the world of AI right now. It's that whole computational demand of self-attention, especially when you're working with these really long sequences.
Right. Yeah, as sequences get longer, self-attention gets more and more computationally expensive, and that can really limit its scalability.
Exactly. And that's where this paper kind of shines. It's proposing to use the Fast Fourier Transform, or FFT, as a more efficient alternative.
And the FFT is known for being really fast for signal processing, but the question is, can it really match the nuanced capabilities of self-attention?
Right. Can it really, hold a candle to the power of self-attention?
Right.
That's what we're going to be looking at today. And you know what? In the first minute, let's just give a quick rundown of the key insights of this paper for our listeners who are a little bit short on time.
Okay, sounds good.
So essentially what the authors have done is they've developed this model called FFTNet. And it leverages the FFT to achieve, global token mixing. And they do this with, remarkable efficiency.
Yeah, it's really interesting how they do it. They actually transform the input sequence into the frequency domain using the FFT.
Okay.
Then they introduce this learnable spectral filter, which is shaped by the input's global context, and that filter modifies the frequency.
Oh, so it's kind of like a smart equalizer?
Exactly, and then they apply the special activation function called modReLU, which is interesting because it operates on complex numbers.
Complex numbers, huh?
Yeah, and this adds this whole other layer of expressiveness that you don't get with traditional linear transformations.
Okay, so we've got the FFT, we've got the spectral filter, we've got modReLU. What happens next?
Well, then they use an inverse FFT to bring everything back to the token domain.
Okay, so they take it to the frequency domain, they do all this cool stuff, and then they bring it back.
Exactly. And what makes this approach so exciting is that the FFT operates in O of n log n time, which offers, some significant speed advantages over self-attention, which is O of n squared.
Right. Yeah, that's a huge difference, especially when you're talking about really long sequences.
Absolutely. And it's not just about speed. The paper also shows that FFTNet can actually approximate the behavior of self-attention. So it's capturing those crucial long-range dependencies while being much more efficient.
Wow. So it's not just a cheap trick. It's actually trying to do what self-attention does, but in a faster way.
Exactly. And they even show that it performs really well against transformers and FNet on the long-range arena benchmark and ImageNet.
Oh, wow. So they've actually put it to the test.
Yeah, they have. And the results are really promising.
So it sounds like FFTNet could be a real game changer for AI.
It could be. For those of you with a bit more time, let's dive deeper into the nuances of FFTNet.
That's good. Let's unpack it step by step. So you mentioned this idea of transforming the input sequence into the frequency domain.
Right.
Could you break that down a bit further for us, for people who may not be as familiar with signal processing and stuff?
Sure. So think of it this way. When you listen to music, you hear a blend of different frequencies, right?
Right.
Well, the FFT is like breaking down that music into its individual frequencies.
Okay.
So it allows us to analyze and manipulate each component separately.
Interesting.
And in FFTNet, the input sequence, whether it's words in a sentence or pixels in an image, is treated like a signal.
Okay.
And the FFT allows us to view and process it in the frequency domain.
I'm with you. So far, we've transformed the input into its frequency components. What's next?
So here's where the real magic happens. They introduce a learnable spectral filter.
A learnable filter. Okay.
Yeah, and this filter is unique to each input, and it shapes how those frequencies are emphasized or attenuated. It's like having an intelligent equalizer that adapts to the specific content of the input.
So it's not just blindly applying the FFT. There's an element of learning and adaptation based on the input. I'm starting to see how they're trying to mimic the dynamic nature of self-attention here. But you also mentioned this modReLU activation function. Why is that significant?
So modReLU is interesting for a couple of reasons. First, it operates on complex numbers.
Complex numbers, okay.
Yeah, I know it might sound a bit intimidating, but they're essential here. They allow us to represent not just the magnitude of each frequency, but also its phase.
Sure.
And this phase information encodes the relationships between different frequencies, adding a whole new layer of expressiveness to the model.
Wait, so you're saying those complex numbers aren't just a mathematical quirk, they're actually encoding crucial information about the relationships between frequencies. That's pretty mind-blowing.
Exactly. It's like understanding not just the individual notes in a musical piece, but also the timing and rhythm that give the music its structure and feeling.
Wow. And that's what modReLU helps us capture.
All right, so we've transformed the input, applied this adaptive filter, and even thrown in some complex number magic with modReLU. What's the final step in this FFTNet process?
Oh, we need to bring everything back to the original domain.
Right.
And that's where the inverse FFT comes in.
Okay.
It essentially reconstructs the sequence, but now it's infused with the global context that was captured through those manipulations in the frequency domain.
That's quite a journey, but some folks might be skeptical, why go through all this trouble? What's the big advantage of FFTNet over traditional self-attention?
Well, as we hinted at in the beginning, the biggest win is efficiency.
Okay.
The FFT at its core is an incredibly efficient algorithm. It processes sequences in O of n log n time.
Right.
Which scales much better than self-attention's O of n squared.
Yeah, that's a big difference.
This means FFTNet can handle much longer sequences without breaking a sweat, opening up possibilities for tasks that were previously computationally prohibitive.
So it's all about speed, just a faster way to crunch the numbers.
Yeah.
It's not just about speed. The paper actually argues that FFTNet can approximate the behavior of self-attention.
Oh, really?
Yeah, it can capture those crucial long-range dependencies that make self-attention so powerful.
Really? How does it manage to do that? I mean, I'm having a little trouble wrapping my head around how messing with frequencies can achieve something similar to, those intricate pairwise comparisons in self-attention.
It comes down to a pretty clever connection to the world of convolutions.
Okay.
There's this fundamental principle called the Convolution Theorem, and it states that filtering in the frequency domain is equivalent to performing a special kind of convolution in the original domain.
Right.
And remember that learnable spectral filter we talked about in FFTNet?
Yeah.
Well, that's essentially creating an adaptive convolution.
Oh,
It's not a fixed convolution like we often see. It's tailored to each input, bringing it closer to the dynamic nature of self-attention.
Okay. So by manipulating frequencies, they're essentially doing this very specialized convolution that adapts to the input.
Got it.
But why is that better than just using a plain FFT? I mean, we've seen other models like FNet try that approach.
Right. That's a great point. So FNet is a simpler approach where they just swap out self-attention with a fixed FFT.
Yeah.
It gains speed, but it lacks the nuance and adaptability of FFTNet.
Okay.
That learnable filter is key. It's what makes FFTNet context aware, allowing it to respond to the specific content of the input.
So it's like the difference between using a generic filter on a photo versus one that intelligently adjusts based on the image's content.
Exactly. Perfect analogy.
That helps a lot.
Yeah.
So it sounds like the authors are really on to something here. But, I'm always a bit wary when a paper makes these bold claims. Did they actually put FFTNet to the test? Did they actually, make it prove itself?
Oh, absolutely. They didn't just stop at the theoretical level. They ran FFT through a whole battery of benchmarks to see how it stacks up against the competition. Right. Okay, I'm all ears. Tell me, how did FFTNet perform in these trials by fire?
It did surprisingly well. They used the Long Range Arena Benchmark, or LRA for short.
Okay.
And it's specifically designed to test how well models handle long sequences, which is, where self-attention really struggles.
Right. And what were the results? Did it beat those computational behemoths?
It actually did, for example, on the listops task, which involves processing these long sequences of mathematical operations. FFTNet achieved much better accuracy than both the standard transformer and FNet.
Wow.
And it also showed strong performance across a variety of tasks, things involving text retrieval, even image processing, which really demonstrates its versatility.
That's impressive, but I'm particularly interested in its image processing capabilities. You mentioned something about FFTNet VD earlier.
Yes, they adapted FFTNet for image recognition tasks and called it FFTNet VT.
Okay.
And get this, on ImageNet, FFTNet VT often beat the standard VIT in terms of efficiency. It achieved similar or even better accuracy while using significantly fewer computational resources, especially for the larger model variants.
So they're showing that this approach isn't just a theoretical curiosity. It can actually deliver, real practical results across diverse domains. It's really compelling.
Exactly. And what's even more impressive is that they didn't just, throw a bunch of techniques together and hope for the best. They actually delved into the theoretical underpinnings of why FFTNet works so well.
Oh, tell me more about that. I always appreciate it when researchers really connect their methods to solid theoretical foundations.
Yeah, so they leverage some pretty powerful mathematical properties. For instance, the orthogonality of the FFT is key.
Yeah.
What this means is that each frequency component is independent of the others. So when you modify one frequency, you're not messing up the information encoded in other frequencies.
I vaguely remember orthogonality from my linear algebra days, but why does that matter in this context?
Well, because of orthogonality, each token in the input sequence gets to influence all the frequencies independently. It's like ensuring that every voice in a choir gets heard without interfering with the others.
Oh, okay.
This helps capture those global interactions that self-attention aims for, but in a much more efficient way.
Ah, that makes sense. It's like a well-coordinated orchestra where each instrument plays its part harmoniously. And I remember you mentioning Parsifles Theorem earlier. How does that fit into the picture?
Right, so Parsifles Theorem guarantees that no information is lost during the transformation to and from the frequency domain.
Okay.
It's like a round trip where you pack your suitcase, you travel to a new place, and you unpack everything without losing a single item.
Right.
This ensures that the output retains the essence of the original input, even after all the manipulations in the frequency domain.
So they've got the global interaction thanks to orthogonality, and they've got no information loss thanks to Parsifles Theorem. It sounds like a really solid theoretical foundation for their approach. But all this talk about frequencies and transformations makes me wonder, what does that spectral filter actually learn?
That's the heart of it, isn't it? It's not just randomly tweaking frequencies, it's learning to emphasize the frequencies that are most relevant to the task at hand. Imagine trying to have a conversation in a noisy room.
Right.
You instinctively focus on certain frequencies, the ones carrying the voice you're interested in, and you filter out the background noise.
Right.
Well, the spectral filter is doing something very similar. It's learning to pick out the signal from the noise in the frequency domain.
So FFTNet is like an intelligent listener that learns to tune in to the right channels to extract the most important information. That's a really neat way to think about it.
Exactly, and that's where the power of modReLU comes in. Remember those complex numbers? They're encoding phase information, which captures the relationships between frequencies. It's like understanding not just the individual notes in a song, but also the rhythm and timing that give the music its soul.
That's a great analogy. It helps to visualize why those complex numbers are so crucial. They're adding another layer of understanding, allowing FFTNet to capture those subtle interactions between frequencies.
Precisely, and to make sure every piece of the puzzle was truly contributing, they conducted a series of ablation studies where they systematically removed or modified different parts of the model to see how it impacted performance.
Ah, the classic, take it apart and see what happens.
Yeah.
Approach. What did they learn from these experiments?
Well, they found that each component of FFTNet plays a vital role removing the spectral gating, which controls the flow of information between frequency bands, or the adapted module hurt accuracy significantly.
Interesting.
But the most dramatic drop in performance came when they replaced the FFT with a standard convolution.
Interesting. So it really is the unique properties of the FFT that make FFTNet tick.
Yeah.
But I'm still curious about how those ablation studies tie back to the comparison with FNet. You mentioned that replacing the FFT with a standard convolution led to the worst performance, which seems to highlight why a simple FFT like an FNet isn't enough. Can you elaborate on that a bit more?
Absolutely. So in FNet, the FFT is fixed. It's applied the same way to every input regardless of its content.
Okay.
It's like using the same wrench for every bolt, even if they're different sizes. You might be able to loosen some, but you'll strip others and get nowhere with some.
I see. So FFTNet is like having a set of adjustable wrenches that can adapt to the specific bolt you're working with. It makes perfect sense why that adaptability would be so crucial for achieving both efficiency and accuracy.
Right. And, you know, that really highlights the brilliance of FFTNet. It's not just about blindly applying the FFT, it's about using it in a smart, adaptive way.
Yeah, it's like FFT++.
Exactly. So where does all this leave us? What's the big takeaway for our viewers who are, you know, working on the cutting edge of AI?
Yeah, what should they be thinking about after listening to this deep dive?
Well, I think the main takeaway is that FFTNet is a serious contender in the quest for, you know, more efficient AI models. It's not just a theoretical curiosity. It's grounded in solid mathematical principles, and it's backed by some really impressive empirical results. You know, it really challenges the assumption that we need those computationally expensive self-attention mechanisms to capture long-range dependencies.
It's exciting to see researchers really pushing the boundaries like this.
Yeah.
And it also makes me wonder, where do we go from here? What are the next steps for FFTNet and for this whole idea of using, you know, frequency domain approaches in AI?
That's the big question, isn't it? This paper focuses on using FFT to approximate self-attention.
Right.
Which is a great starting point. But what if we could move beyond approximation? What if we could develop entirely new mechanisms that are native to the frequency domain? Mechanisms that might even outperform what we can do in the token domain.
That's a fascinating thought. It's like we've been exploring this vast continent of AI, and suddenly we've stumbled upon this hidden doorway leading to a whole new world. Who knows what kinds of amazing discoveries await us in this unexplored frequency domain territory.
Exactly. Maybe we'll find completely new ways to process information, to learn from data, to build even more powerful and efficient AI models. This paper has opened up a whole new avenue of exploration, and I'm really eager to see where it leads.
Me too. It's a good reminder that there's always more to learn, more to explore, more to discover in this ever-evolving field of AI. Who knows? Maybe some of our viewers will be the ones to make the next big breakthrough in frequency domain AI.
Absolutely. And we'll be here to cover it when they do.
So to all our viewers out there, we encourage you to check out this paper, dig into the code, and see what you can discover.
Yeah, have fun with it.
And on that note, we'll wrap up this deep dive into FFTNet. We hope you found it insightful and inspiring. Until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible with AI.
See you in the next episode.